So a projectile is any object that we give an initial velocity and then it just flies through the air while the only thing acting on it is gravity. And so remember in the last video we came up with a bunch of kinematics equations to describe motion at constant acceleration along a straight line. So in order to use those equations in this two-dimensional situation, this projectile is moving in the x direction and the y direction. All we have to do is look at the x motion and the y motion separately. And then we can apply these same equations that we came up with to the x and y motions of this projectile. And the acceleration is constant because the only acceleration that this projectile has is due to gravity. And we know that gravity is always vertical. So the acceleration due to gravity is always only going to be on the y direction. So which means the acceleration in the y direction is going to be a constant negative 9.8 meters per second squared, assuming we choose down as the negative y direction. And then that means the x component of the acceleration is going to be 0. There is no acceleration in the x direction, only the y direction. So we can use the displacement equation. Displacement equals initial velocity times t plus 1/2 at squared. We can apply this equation to the x motion and the motion in the y direction separately. But first we need to split up the initial velocity to find out what part of this initial velocity is in the x direction and what part of it is in the y direction. And so we can do that if we know the angle that the projectile is launched at, relative to the ground. So if we launch the projectile with an initial velocity v0 and at an angle theta, then we can write that the x component of this initial velocity is cosine theta times VO. Because, cosine theta is just adjacent over hypotenuse, which is VOX divided by VO. So if we multiply cosine of this theta by VO, we just get VOX, the x component of the initial velocity. Likewise, we can find the y component of this initial velocity vector by doing sine of theta multiplied by the initial velocity. So substituting these expressions into the displacement equations, we can find the equations for the motion along the x-axis and the y-axis. Since we know that along the x-axis the acceleration is always 0, so we just ignore this term. And along the y direction, the acceleration is always negative 9.8, which is negative g. So these are going to be the displacement equations we use to analyze the x and y motions of a projectile. So now let's look at an example. We have a ball thrown at 37 meters per second, that's the initial velocity, at an angle of 53.1 degrees relative to the ground. So the first thing we want to know is what is the velocity at time equals 2 seconds. So the first thing you always do in a projectile motion question is find the x and y components of the initial velocity. So that way you can use these equations. So the x component is just the initial velocity 37 times cosine theta, which is 53.1, and then the y component is just VO times sine of theta. So we find these, and now we can use the equations to find the new velocity after a certain time. So we know that in the x direction there is no acceleration, so this initial velocity in the x direction is going to stay constant throughout the projectile's flight. And then for the y velocity, we just used velocity is going to be equal to the initial velocity plus acceleration times time. Remember, acceleration times time, it represents a change in velocity. So using this equation, we can find the final velocity in the y direction after 2 seconds. And so once we have the x and y components of the velocity, we can find the overall magnitude and direction of the velocity vector at 2 seconds. So the magnitude is just going to be from the Pythagorean theorem. It's going to be the square root of the x component squared plus the y component squared. And then now we can find the angle at which this velocity vector is pointing, because we know that the tangent of this angle is going to be opposite over adjacent, which is the y component of velocity, which we found to be 10, over the x component of velocity, which is still 22.2. So we can use arctangent of 10 over 22.2 to find the angle of the velocity vector. And so notice how the angle is much smaller than the original angle, which is what we'd expect, because at time equals 2, the projectile may be somewhere around here. So the angle is of the velocity vector is going to keep getting smaller and smaller until it reaches 0 at the maximum height. And then after that point, the projectile starts going down. So next we want to know when and where does the ball reach its maximum height. So at the highest point, the y component of velocity is equal to 0, because after this instant, this y component of velocity starts to turn negative, so the projectile moves downwards. So we can use this same equation, setting the y component of velocity here equal to 0, and then rearranging to find t. And then we can find the displacement at this point just using the equation for displacement and plugging in this value of t that we just found. And lastly, we want to know when and where does the ball hit the ground. So when the ball hits the ground, it comes back to the point where we threw it. Not the same point, but the same height. So the displacement in the y direction when the ball hits the ground is going to be 0. And so then we can use the displacement equation, setting it equal to 0 and solving for t. And this is a quadratic equation, which means it has two solutions, because of course the ball reaches this height 2 times in its flight. Once when t equals 0, which is when we just throw up the ball, and then it comes back down to the same height after a certain time. So either this can be 0 or this whole thing can be 0. And so we solve for t in this expression, and we find that it's 6.04 seconds. So the projectile is at 0 y displacement at time equals 0 seconds and 6.04 seconds. And then to find how far horizontally the projectile traveled when it hits the ground, we just use the displacement equation in the x direction, using this time that we got when the ball hits the ground.